Notes 5.3, talking about logarithms and their properties. We know that 2 to the third power is 8, okay? Because 2 times 2 times 2 is 8, right? So what we do is with logarithms, we say that 3, that exponent there, is the logarithm to base 2 of 8, okay? And we can write it like this. So that exponent is equal to log base 2 of 8, okay? Logarithm is an exponent, so properties of exponents apply. Okay, so first of all, let's go back and forth with it. Let's rewrite this in log form. Okay, so we have to think about what's the base of it, what's the number here, what's it equal to. Okay, I think when I personally do it myself, I think base raised to the outside equals the inside part. Okay, so this is my base, this is my outside part, equals the inside part. So I would say log of 1/2 is of 16, log base 1/2 of 16 is equal to -4. Okay, so the next one there, okay, so just keep thinking, base raised to the outside part equals the inside part. That's what I think anyway. So my base is base 10 of the outside part equals the inside part. Whoop, I'm sorry, equals. Base raised to the outside part equals, okay? So anything to 0 power is 1, okay? So we have that there. So we would say log base that of 1 is equal to 0, okay? And really we could say any base, log any base of 1 is going to equal 0, isn't it? Because anything to the 0 power is going to equal 1, okay? So here we would say log of the base, the outside part, okay, log base 3 of 1/81 is equal to -4. So that's how we can rewrite all these exponents as logs. Next section, we're going to write these as exponents, and then we're going to solve them to solve for the x. So I keep thinking base raised to the outside part equals the inside part. Okay, so what squared is equal to what is equal to 4? We know that 2 squared is equal to 4, right? So x is equal to 2. Well, remember how we did this the other day? We've got the same bases, right? So I know that x would equal 2. Okay, so this one here, base raised to the outside part equals the inside part. So we think what number to the 4th power is equal to 16? And it's positive or -2. One way you could do that is take the 4th root of both sides, right? Remember, a square root you put plus or minus, 4th root you put plus or minus, 6th root all evens, because whenever you take a positive or a negative, it's going to equal the positive there. And then here we have our base raised to the outside part is equal to the inside part. Okay, so then when you work that out, if you remember, 1/2 power is the same as the square root. So it would be 2, and then 2 to the 3rd power is 8. Okay. Next, we're going to talk about the common log. Okay, so it used to be that calculators only had log of x. They didn't let you put different bases to them. So what we have here, if something called the common log is just log of x, implies that it's log base 10. So if there's nothing written there, it's implied that it's base 10 of x. Okay, so this is really the same thing as log base 10 of 12. And to evaluate that, it's nice that Desmos and actually the updated TI calculators do this. You can put different bases in for those, but if you go under Desmos, pop up your screen from the bottom, and if you go under functions and then miscellaneous, you'll see both log and you'll see log base A. Okay, so you can do them both ways. So this is just log. Okay, so here we're doing log of 12, and it's approximately in your calculator 1.079, and log of this is equal to -1. Okay, and log of 3/5 is approximately -0.222. Okay, it's like 1/8 or something. But if I go to the thousandths place, okay, that's how we do those there. So a little bit of applying here in chemistry. The pH is this equation. It's negative log of the hydrogen ion concentration in moles per liter. Okay, but it's a log function. It's based upon a log function. So if you have 7 or above, it's alkaline, and if it's 7 below 7, it's considered acidic. Okay, so if our concentration is this, is it alkaline or acidic? Okay, so what we can do, our pH would equal negative log of 2.5 times 10 to the negative 4. Okay, so in working that out, you can use a calculator for that. We find that it's approximately 3.6. So pH generally goes to the nearest tenth is what they usually do. So it's less than 7, therefore it is acidic. Okay, next one here says find this concentration if we know the pH is 7. So 7.1 equals negative log of what we're trying to find. I'll just call that x. Okay, if I get rid of that negative, okay, so we get this. Now remember, this is base 10, right? So I could say 10 to the negative 7.1 is equal to the x, right? Base raised to the outside equals the inside part. Okay, that sort of idea. And if I work that out, 10 to that power, it's like 7.9 times 10 to the negative 8. So it's a incredibly small number. Okay, but that would be that concentration there. The other type of logarithm, so we talked about just like the normal log, we talked about the common log, which is base 10. The other is called the natural log, and logarithms with base e. We talked about this e the other day, right? This e number was like 2.079 blah 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 blah, right? Okay, so we have this number e that actually shows up quite a bit in a lot of natural things. But anyway, so the natural log of x is considered log base e of x. Okay, so if you see NL, natural log, that means that it's base e. Okay, that it's base e. So if we want to evaluate this right here, you can go to Desmos again, and the same place you found the log under functions, you can find the natural log as well, ln. So the natural log of 12, if you evaluate that, is like 2.485. Okay, it's irrational, it kind of keeps going. Okay, what happens is the natural log and e, they're inverses of each other, they cancel each other out, so this would just be 10. Okay, and here, this would be the same thing as natural log of e to the 1/2. And once again, remember, the natural log and e cancel each other out, so you just have 1/2 as your answer. Okay, so if you remember the other day we did this compounded continuously. The amount equals our principal that we put in, e raised to the rate times the time. Suppose we took $1,000, invested it at 3% annual interest, compounded continuously. How long will it take for it to grow to $1,500? So we don't know where it's equal to $1,500. So we're starting with $1,000. It's continuously, so we're using this e. The rate is 0.03, and our time is what we want to find here. Okay, so the first thing I would do is I would divide by this 1,000. So I get, what, 1.5 is equal to e to the 0.03t. Okay. Okay, I had said that natural log was kind of the inverse of these, of the e. So if I take the natural log of both sides of the equation, I'll have ln natural log of 1.5, and natural log and e cancel out, so I just have 0.03t. Okay, and then to get t by itself, I divide by this, so I have natural log of 1.5 divided by 0.03. That's the exact answer. If you put that in your calculator, it's about 13.5. So after 13 and a half years, that $1,000 would turn into $1,500. Okay, now if I want to do this graphically, I'm going to pause this and get a graph and see what it looks like. Okay, if we want to solve it graphically using Desmos, I'm going to take this equation. I'm going to subtract to get it equal to 0, so I'm going to subtract the 1,500 over, so I have it equal to 0 now. And if you graph this, remember how you should probably put that in parentheses up there, and you get a graph that would look like it goes right through there at 13.5. So graphically makes it pretty easy. Just set the equation equal to 0 and solve. Okay, these are different properties of logarithms that you really need to be familiar with and know. You might want to put these on a little cheat sheet sort of thing that you can refer back to a lot. 1, if we have log base a of 1, it's going to equal 0. Basically, we kind of saw this before. If I turn this into an exponent, I know that any number raised to the 0 power is equal to 1, right? Okay, so that kind of follows from that equation there. Property 2, we can kind of think of it as, if I turn it to exponent, remember that to this power, right, is equal to the inside part. So we can see that a to the k is equal to a to the k. Property 3, you can kind of think about that as this is the exponent that a has to be raised to in order to get k. So if we think about that, just be familiar with that property there. These other 3 actually are so important, they actually have rules. Okay, the product rule, the quotient rule, and the power rule. Thinking about remember when you multiplied with exponents, right? You added the exponents, right? Okay, when you multiply, you add. So we can kind of think about that here. If I take the log base, it could be any base, of x times y, we can rewrite that as log base x plus log base y. Okay, so we have the addition there. When you multiply, you can separate them into addition. And remember when you divide, so for example, like, remember if we do exponents like x squared times x to the third, right? That's x to the fifth. Okay, thinking that's kind of explaining this one right here. You add here. And if the quotient rule, remember when I divide, I can think I subtract here, right? 3 minus 2 is 1. So when I'm dividing, I can think of it as any base of x minus the y there. Okay, and if you think about the power rule, if I have x to the third squared, I know exponent to an exponent, I have to multiply those, right? So you can think about that here. If it's x to the r, I can take r times that exponent or that log. Okay, so those rules right there are pretty important. So let's think about this here and use these to rewrite them. Okay, this is a multiplying. So remember when we are multiplying, we can separate it into an addition. So we can say this is log of 8 plus log of x. Remember, if it's just log with no bases, it's implied base 10. Okay, we don't really need to know that here, but that's implied. Okay, remember when we divide, we can make it a subtraction. So it's log base a, whatever, of 15 minus log base a of 7. Okay, this one here, another way to rewrite this is log base 5 of 8 to the 1/2. And I know if I have, using the power rule, this exponent here makes it a multiply problem. So we can say this is the same as 1/2 of log base 5 of 8. Okay, this one here, 0.1 is the same as 1/10. Okay, so if I think about this as a division, if it's a division thing, yeah, actually, let's actually put it as a negative exponent. So this would be the same as 10 to the negative 1. So remember, yeah, so if I rewrite this, I can say, remember this is the base 10, right? So this would be the same as 10. Actually, we can let's do this. Let's think this as the log base 10 of 10, those are kind of inverses of each other. So my answer is really just that exponent of negative 1. Okay. This one here, if I use this one right here, okay, using rule number 3, I know that it is equal to 3. Okay, so those two will cancel out there. Okay, the next one there, if I'm dividing, remember I'm dividing, I can use the quotient rule. So this is log base A of x minus log base A of yz. Okay, that's a quotient rule. And then remember, when you're multiplying here, we can use the product rule. So when you're multiplying, you can separate it into addition. So this would be log base A of x, and remember it's subtracting of both of these, right? So minus log base A of y, and it is a plus, but since I'm distributing this negative through to both of them, it's going to be minus log base A of z. Okay. Let's rewrite this one with an exponent. So this is the same as log base A of m to the 2/3. Okay. Now, with an exponent here, I can use the power rule and bring it out front. So this would be 2/3 times log base A of m. Okay, this one's going to be a little bit longer one because there's a lot of stuff going on here. Okay, so first of all, let's say let's get rid of the, this is log base b. Let's get rid of the square root thing here, or not square root, but root thing. So we have x to the third, y to the fifth over z to the m. This would be to the 1/n. Okay, if we get rid of the root part, I can bring that out front. So it'll be 1 over n times this. Okay, now I can think about the division stuff here. So this would be 1 over n log base b. Okay, division, I'm using the quotient rule, which is a subtraction. So it'd be x to the third, y to the fifth, minus log base b of z to the m. Okay, so here I can take this and I can use the product rule and change it to be addition here. So I have 1 over n for log base b of x to the third plus 1 over n log base b of y to the fifth minus, okay, and this one here, I can take this exponent and put it out front too. I could actually do that with all these here, and I'm going to do a little bit. Log base b of z. Okay, now I ran out of room here, but I'm just going to put it right here. If I take this exponent and bring that out front times the 1/2, it'd be 3/2. So it'd be 3/2 of log base b of x. Bring this 5 out front with the 1 over n using the power rule. So it would be 5 over n log base b of y. And if I distribute that n through here with this one, sorry, that should be in there, it'd be m divided by minus m over n log base b of z. Sorry, that is not very neat there, but I should have wrote it a little smaller at the top. Okay, so using those properties there. Now, let's take it the other way. Let's take it as something expanded and write it into more something like this. Okay, so this first one here, if you adding, okay, we can think about that as the product rule. So we can say this is log base 3 of, okay, so these two right here, adding is the product rule, right? So there's more like multiplying this together. This would be x plus 2 times x. And then since it's subtraction, I can use the quotient rule. That's the same thing as this. So we're just divide by, well, I should put that not there, right there. Okay, so with the addition part, that makes multiplying from a product rule. Subtraction is the quotient rule. So log base 3 of this. Okay, number 2, Okay, so the 2 out front I'm going to put up here with the using the power rule that we did. So this would be m squared minus log base a of n to the 3rd power. Okay, using the product rule, power rule. Now since it's subtraction, I can make it the quotient rule. So log base a of m squared divided by n to the 3rd. Okay, next problem here. First I'm going to take care of the numbers out front using the power rule. So I log base b of m to the 1/2 plus log base b of 2n to the 3/2 minus log base b of m squared n. Okay, so since this is addition, I'm going to use the product rule. So this is log base b of m to the 1/2 times 2n to the 3/2, and since it's minus, using the quotient rule, that's going to be like the division, m to the 3rd n. You could leave it like that, or we actually want to let's take this part and simplify the m and the n's. So this would be log base b of m to the 1/2 times 2 and n to the 2 to the 3/2 and n to the 3/2. And this would be m squared and n, right? So if I reduce this stuff here, so if I take 2 to the 3/2, that'd be like the square root of 2 to the 3rd is like square root of 8. We'll just, for this step, we'll just leave it as this right now though. Let's take care of these m's and n's first. And remember, when we divide, we're going to subtract. So 3/2 minus 1 would be 1/2. And the m's subtract, that minus that would be negative 3/2. So I'm going to move it to the bottom and make it 3/2 there. Okay. Now, since they're both halves, I'm going to make this the square root. Okay, so square root of 2 to the 3rd is 8, and n, and m to the 3rd. Okay, so 1/2 power makes them all square roots. Okay, the next rule we're looking at is the change of base rule, and this used to be extremely important, especially before you could put like when calculators only did base 10 and base e, so common log and natural log. Now the calculators and Desmos and stuff has different bases that we can evaluate, so we could just type this in the calculator and get an answer, right? But before, you should know this anyway, before we could change these to base 10 or natural log by using the change of base rule. So if we want to change this base, we can use this formula. So log base a of x is equal to log base whatever you want of x divided by log same base of a. So if we use the log function, we could say this is log base 10 if we want to, or you could make it any base you want really. Log base 10 of 17 over the log of 5. Okay. You could also say this is, if you use natural log, okay, that's another one that's easy to do in the calculator. We can say this is the natural log of 17 over the natural log of 5. Okay, both of those things give you the same answer, which is approximately 1.760. Okay, so same idea here with this one. If you work this one out, we could say this is the log of 0.1 over the log of 2, which is the same thing as the natural log of 0.1 over the natural log of 2. And really you could say it's the same as any base. You pick log base 100, okay? But this one, if you would work this out, it comes up to be approximately negative 3.32. If you go to 3 decimal places. Okay, so that is section 5.3.